I've explained. So
सरस्वती नमस्तुभ्यं वरदे कामरूपिणी विद्यारम्भं करिष्यामि सिद्धिर्भवतु मे सदा पद्मपत्रविशालाक्षी पद्मकेसरवर्णिनी नित्यं पद्मालयां देवी सा मां पातु सरस्वती भगवती निःशेषजाड्यापहा
Hello, friends. Welcome all. I'm very happy to share start our pre-conference academic webinar. Just to begin with, to tell you that we are just nearly a month away from our annual meeting. This annual meeting is going to be a great academic feast. Lot of international speakers are coming. Very good, excellent topics, and there will be a good chance of interaction with all the faculties. So in case if you have not registered, please do that fast. We have a lot of good industry participation, and one of the company is AI for medical imaging, and we are having our pre-conference academic webinar. I invite Dr. Ashita Barthur from Jaydeva Hospital to moderate the session.
thanks, Priya. Thanks for the opportunity. And thank you, Dr. Pereira, for being here for this pre-conference session. So to introduce Dr. Vitor Hugo Pereira, he's a cardiologist at the Hospital of Braga and an assistant professor at the School of Medicine, University of Minho. Since completing his PhD in 2014, he has dedicated his time to clinical research. VHP is enthusiastic about leveraging artificial intelligence to enhance medical imaging and improve clinical outcomes and the daily workflow. He is the co-founder and CEO of AI for Med Imaging, a deep tech company that develops machine learning algorithms for the automatic interpretation of cardiac magnetic resonance imaging. Thank you for coming again, and over to you.
Okay, Sita, thank you very much for the introduction, and good evening, everybody. Still good afternoon here in Portugal. So it's really a pleasure being here, and I'll start by sharing my screen. Just let me know if you are if you can see my screen correctly.
Yeah, we can. Yes.
Okay, great. So today I'm going to talk to you about the new frontiers in cardiac imaging and how artificial intelligence and cardiac magnetic resonance actually are changing the game in cardiac imaging. So I'm going to start by introducing myself a bit more. So I'm coming from Portugal, just facing the Atlantic Ocean, from a small but beautiful city called Braga. You can see some of the pictures here around, and of course that you are invited to visit if you happen to come to Portugal. In terms of my career, I have to mention here two main institutions. So the School of Medicine at University of Minho in Braga, and also the Hospital of Braga. So this is where I split my time in terms of the clinical work and also my academic career. And actually, when I started my academic career, it was not that much related with cardiac imaging. At the time, I was really interested in understanding how chronic stress and mental health diseases were affecting the cardiovascular system. So if you go check online, you'll find some of my papers on the field about how the brain influences the function of the heart. But then when I finished my residence in cardiology, so I'm a cardiologist by training, I got in touch with cardiac MR. And to be honest, I got a bit fascinated, not a bit, I got fascinated with the technique. So I started to invest in the field, my time in the field, and I started to do training in cardiac magnetic resonance. And you'll see that's how everything started. So when I started my training, I started dealing with the difficulties in the field. So I was finding it really time consuming to do the report of a single exam. When I did my training, the fellows were spending a lot of time doing the segmentation of the heart. And even after doing the segmentation, usually the expert was going there and checking if we are doing everything correctly. And it was not uncommon that adjustments had to be done. So sometimes we were losing 45 minutes, even more, just to segmentate a single patient. So I found this a bit demotivating at the time, but since I was still in training, it was giving him I was feeling special that I knew how to do this, but at the end of the day, it was not productive. Then I also felt another limitation of the technique is that even if it's the gold standard for the determination of volumes and ejection fraction, the interpretation is still subjective. So, and what is described in the literature is that the inter-observer agreement is only around 85%, even among experienced readers. So I was finding myself a lot of times, and I'm sure it happened with you, discussing with peers if this is normal, if this is abnormal, if the wall motion is normal, or if there's any hypokinetic segment or a kinetic segment. So I was finding this also a bit challenging, because it's an exam that it happens to be most of the times the end of the line in terms of diagnosis. People request it for taking the final decision. So I was, facing these challenges at the time. And then when I finished my training and I was ready to implement a cardiac MR program, I started to face the problems of the implementation of a program. So, of course, that we cannot implement a cardiac MR program without having software for the post-processing of the images that we acquire. And Usually the workflow is that, of course, the images are acquired, they go to the PACS, to the archiving system of the hospital, and then usually they go to, let's call it a cardio viewer. It can be a cardio viewer from the vendor of the MRI equipment. And then we spend there a lot of time doing the manual and the segmentation or the semi-automated analysis, and only then we can do the reporting. So having this in mind and facing this challenge, and knowing that the Society for Cardiovascular Magnetic Resonance was also pushing for shortening the examining time, I gathered with a couple of people, and I'm going to explain, to tell you who, to try to develop a tool that would overcome these challenges. Okay, so just to explain a bit more, what are you watching here? So this is a paper from the Society for Cardiovascular Magnetic Resonance, where they describe an acquisition protocol that will take less than or around 20 minutes of time in the machine, so that we can increase the productivity of cardiac MR. But then you still have to report it, and really reporting really takes a lot of time. So having all this in mind, I gathered with a group of engineers. They were working in artificial intelligence, but they were not working in healthcare. They were working in other fields. But at the time, we had ongoing conversations with university and this group of engineers to develop a common project in health. And they came to me and asked me if I had any idea to do this for a project. And that's how I brought to the table these challenges in the field of cardiac MR and proposed to them, can we develop something to overcome this? And the answer was yes, we can work on that, and we can try to help you with this need that you are facing every day. And if you are facing it, for sure, others are feeling the same. So what did we do? So basically, like I mentioned, I was also working at hospital. So we took around of 1,000 cases from its real life, daily patients from the hospital, of course, fully anonymized. So this is real world clinical data. We got these CMR cases, all labeled by CMR experts. So they were annotating the cases, doing the segmentation. And not only doing the segmentation, they were also classifying the wall motion of the cases. So telling us if the wall motion was normal or abnormal. And our data set, as you can see here, and I mentioned this before, it's a real world data set. So it's composed of around 2/3 of male, 1/3 female, due to the prevalence of cardiovascular diseases in both genders. And you can see here that the number of absolutely normal cases was a minority. So just 35% of the cases were considered normal. The rest of the cases had at least some pathology. So this is really a differentiator, and this is really important when you start to develop algorithm that is AI based. So, like I mentioned, we got experts doing the segmentation of the heart. They also had to write down the bullseye in terms of the wall motion of the CNS sequences. And then we used state-of-the-art deep learning techniques for extracting the features of the images, then perform the analysis of the features. So we got models that would basically mimetize what the experts were doing, and with the ability, and this is very important, of learn and improve with time. Okay, so the models that we develop, they are accurate, but in the long term, the best thing is that they will keep improving as we train them. So if we start training them again, they will get better and better and better. So The expectation here is that with time, we will be offering and improving. We'll be offering better models, and because we'll be improving our models. So after training and the fine tuning, so that means that this goes in iteration. So you train the model, you get the model, you train with a smaller data set, and if the result is good, so ready to go. If it's not perfect, you can retrain again until you are happy with the result. And if after a lot of training you don't get the result, the only thing you need to do is to increase the number of cases that you have in your data set. So, but at the end, with these 1,000 cases and using this novel technology, we got a model that was performing this kind of segmentation, both for the left ventricle and also for the right ventricle. So, and what is striking here is that this is done without any human interaction. So you don't have to tell the software where is the right ventricle or where is the left ventricle. Things go automatically, and you have the quality of the segmentation that, as you can appreciate, is quite good. Of course, that we had to take a decision if we should include or exclude the papillary muscles from the blood pool. We decided to include the trabecula and the papillary muscles in the blood pool. The recommendations say that you can do both ways, since you tell what you have done. So this was a decision based on what we felt that was more common in the clinical practice. So this is one of the things that the software does: fully automatic left ventricle, right ventricle segmentation and quantification. And of course, that from here you have all the volumes, the ejection fraction, the cardiac output, the LV mass, the LV index, everything. And then it also tells you, or it classifies the case in terms of the global and regional motion of the left ventricle. Okay, so basically, I'm sure that it also happens to you. When I'm reporting a case, what I do is that I do the segmentation, and then I take a look at the CNS sequences. And I'm only happy when the segmentation and the quantification matches what I'm seeing, what we call the eyeballing. So if I do the segmentation and the ejection fraction is below normal, but if to my eye the ejection fraction seems normal, I go back to the segmentation and review if I did anything wrong. So what we also included in the software was this eyeballing. So basically, the software will also eyeball the wall motion of the left ventricle. So, and it will tell you if the left ventricle, the wall motion is normal or if it's suspicious. In case if it's suspicious, you still have to go there, look, and then of course detail the wall motion segment by segment. But it's very useful to screen the normal cases. Okay? So this is so now that we had a software, a model that was working, and we were happy with the results on this data set, we had to go to other data sets and other experts to understand if this was working well or not. So we ran a clinical trial. So the clinical trial included 3 experts. So 2 experts were doing the segmentation and the wall motion assessment of the left ventricle. And whenever these experts were tied, we had different experts to untie the classification. And these experts were compared with the software that we get that we developed at the time, that we call AI for CMR. So we are talking of 150 cases that were assessed, of course different from the initial data set of 1,000 cases, This was done in an hospital in Italy. The leader of the clinical trial was Dr. Lombardi. So when the population was had an age range of 17 to 85 years old, 23% female, 77% male. So the percentage of normal versus pathological cases was around 50-50, and we included cases from the different vendors. So in specific Siemens, General Electrics, and Philips. These are the 3 top MRI vendors in the world. So, and the cases were coming from different centers. Okay, the people were from Italy, from a single center, but the cases were coming from different centers. So, and we measured 2 things. One, how the volumes compared between the experts and the software, and we also quantified how specific and sensitive the software was to classify the wall motion. So, and then here you can see that the interclass correlation that tells you the level of correlation between the assessments was really, really high, around 0.99 for then diastolic and then systolic volume. Also excellent results for the ejection fraction and the mass, and a bit lower for the right ventricle, because the morphology of the right ventricle is different and less typical than the morphology of the left ventricle. And then in terms of this classification of this eyeballing of the heart, the sensitivity was around no, it was 100%. So this means that the software didn't label any case as normal, that the experts labeled as abnormal. Of course, it's an important thing here to mention that this was by design. So we trained the software to be as sensitive as possible, so that when it will say that is normal, we are sure that is normal. Okay. Of course, that this came with a cost, and the cost was the accuracy that was a bit lower than what it could be if we maximized both sensitivity and specificity. Okay. So that means that when using the software, we will get cases that are labeled as abnormal, that then when you eyeball them, you think that they are normal. But we wanted to increase the safety of the software rather than performance. And I'm going to show you more data on this. Okay, so this is again the breakdown of the data set in terms of pathology. So we had around 40% of normal cases, and then we had 30% of ischemic heart disease and 20% of cases with cardiomyopathies or heart failure. And then other pathologies were also represented. So this is the results in more detail. You can see that the difference between the experts and the software in the end diastolic volume was around 8 milliliters. It was around 3 milliliters for the end systolic volume, and the average error for the ejection fraction was around 3%, and for the mass just 2 grams. Okay, if you go to the right ventricle, you get similar results. There were slightly bigger changes in the end systolic volume and also in the ejection fraction of the right ventricle for the reasons I already mentioned. So, like in terms of, again, the wall motion classification, if we maximize the model in terms of the accuracy, we could get a model with an accuracy of 94% for the classification of the wall motion in normal or abnormal. But again, we adjusted the threshold to make sure that we got the highest sensitivity possible, and we got, like I mentioned, a sensitivity of 100%. So this was by design. We could offer a more accurate model, but it would come with the cost of labeling some normal cases that actually were abnormal. So after this study, we still felt that we could do more. And what was missing? It was missing to have an information about the correlation or the comparability, let's say, of the contours of the left ventricle. So how does the contours, the segmentations really correlate with the contours of the experts? So this is a bit different from the volumes, because we can segmentate a bit different and reach the same value. But here what we did was to compare the pixel by pixel, the segmentation of the experts and the segmentation of the software. So what we did was that we used a data set from the Society of Cardiovascular Magnetic Resonance. Actually, it's only 15 cases, but these 15 cases are labeled by 7 experts. So at the end, you have a lot of segmentations to compare with. And then you have a consensus. Okay, so we compared the software, the model that we developed with this. So, and we got the same metrics. So this was just for the left ventricle, because there was no data from the consensus for the right ventricle. And we basically replicated the metrics. So the interclass correlation for the end diastolic volume and the end systolic volume was really high. And we got very, very happy with the results, because the error of the ejection fraction was below 1% when compared with the consensus. But what is more striking is this data here. So the green bar tells you the range of values that you got by the experts. So this means that the experts were disagreeing in this range, what is quite impressive. So in ejection fraction, we are talking about disagreement sometimes of 10% between experts. So this is really striking, okay? So, and the model behaved as an expert, as a human expert. So if we mixed the performance of the model with the performance of the experts, we wouldn't know if it was a software or if it was an expert. And this is really, really striking. This was really, for us, it was really, really exciting. And you can see here the one metric that is called the DICE, that correlates the segmentation pixel by pixel. And the correlation was above 0.8. And this is in this field, it's considered really high. So above 0.75, the correlation is considered really high. And you can see on the red is the segmentation by the consensus. On the green is the segmentation of the model. And you can see that this agreement was more on the basal slices, because the consensus, they were drawing the left ventricle outflow tract, while the model was cutting the left ventricle outflow tract, also by design, okay? Also by design. So, and this is the data in more detail. Like I mentioned, you can see the ejection fraction here is almost in the line of the consensus, so getting excellent results. So basically, these studies were multi-vendor, multi-center. We had 146 clinical cases analyzed by 3 experts, and we got excellent reliability on volumetrics computation, no false negatives on the screening of normal versus abnormal. And this will, of course, optimize the work time when you are doing reporting. But I didn't tell you about how we tackled the third pain that I was suffering at the time, and was the pain of when implementing a program, a CMR program in an hospital, having to go through the pain of getting a software that would work in a workstation. So you were stuck in the computer, you had to work in that computer. Most of the times that workstation was not integrated with the rest of the hospital. So I still have to do that sometimes in smaller hospitals where I have to write down the values by hand and then type it manually in the reporting system. Okay, so this was still to be tackled, and this enters in the phase of the productization of the model that you have. So this is the next step. You have the model, now you have to transform it into a product. And so what did we do? So what we did was that we designed the model to be hosted in the cloud and to be fully integrated with the PACS or the VNA of the hospital. So what happened is that instead of you having let's say cardio viewer from where you have to import the images that are on the PACS and do the manual or the semi-automated analysis, what we have is a cloud that is connected with the VNA. The images go automatically to the cloud, and on the cloud, what happens is this automatic post-processing. So you have automatically the segmentation and this classification, this eyeball classification in normal versus suspicious. And from this, you can export then the results for your report. Okay, if you have to adjust, we have a small viewer that you can open and adjust contours to make sure that you have this according to your criteria, because of course that we always have to validate what the software is doing. So these are a couple of cases that I collected this week. So actually the first two are normal cases. The third one is a patient with heart failure with depressed ejection fraction. And again, you can appreciate the quality of the segmentation. And like I mentioned, this is real life patients that I got this week in my practice. So, and what are we planning next? And I'm also going to tell you what some exciting things that are happening at the moment in artificial intelligence. So this is really well advanced in the pipeline, and the next thing is to get also the atrial segmentation done. You can see the results. So we will get automatically the areas of the atria also. Also the automatic measurement of the maximum thickness of the left ventricle. So we'll also get that work done. And we also have a feature for flow segmentation, and you can see here on green how well it contours the region of interest, and of course then the flow metrics comes automatically. But in this case, you still have to select the vessel or the valve that you want segmented. And this is something that I'm really excited about. One of the features that we are developing is the automatic quantification and interpretation of fibrosis. So what you can see here in the video is on red, the automatic segmentation of the left ventricle, and in blue, you can appreciate the automatic segmentation of fibrosis. And of course that you, when you have these patterns, you can of course also start to play around with diagnosis, because we know that pattern recognition in late enhancement is one of the most important things for the diagnosis using cardiac magnetic resonance. So this is also well advanced in development, but it's still not available. So we are also planning other things to come in the future. Strain quantification automatically. You can already see here a glimpse of what we plan to do, but this is just an idea of this was just basically some models that we have been playing around. And also we want to perform the automatic analysis of the stress perfusion to detect ischemia. This is a less developed than the feature that I mentioned before. But there are also other developments in the field that are not only on the post-processing. There are also others on the acquisition stage. And I'm going to tell you some of the developments that I saw that I really think that are very exciting. And these are not coming from our group, okay? These are from other researchers. So this is a paper, a recent paper, showing how you can actually get super resolution images, but using low resolution acquisition that are faster, of course, than high resolution. So basically what the researchers did was, using artificial intelligence and deep learning, they got low, let's call it low quality images. They ran it through the model and they got images that are well compared with images acquired in high resolution. And when you compare this, these were images dedicated to the coronaries, coronary arteries. You can see how well they compare. These are really, really impressive results. So it's funny because we can actually shorten even more the acquisition time and use sequences that are, it seems that they are low quality, but then using the deep learning techniques, we can improve the quality of the images. And I love this one. This is a very beautiful paper. Let me just, this here. So what you're seeing here, they look like late enhancement images, but actually these were acquired or generated without any contrast. And how? So what they did is that they developed a deep learning model that takes the mapping images, and with the cine images, they generate a late gadolinium enhancement like image that they called virtual enhancement, that are really comparable with the images from the true late gadolinium enhancement. So this is really an exciting paper because it pinpoints that we may achieve similar images without the use of contrast. That's of course also a limitation of cardiac MR. So and it also tells us what artificial intelligence can do, not only in the post-processing, but actually in generating new images. So I really think that artificial intelligence will help us to bring cardiac MR to the front of cardiovascular diagnosis. And of course, that the question that always arises is, so what's the role of the human in this workflow? And don't forget that artificial intelligence is not here to replace anyone, but it's here to help everybody. So at present, and I'm quoting this paper, clinicians' input is mandatory, not only in labeling the data and appraising the developed frameworks, but more importantly, in the decision-making process. So the physician, the expert, still has and will have always the final word, not only to validate the exam, but also to make a final decision on this case specifically on the reporting, but also, of course, on the strategy for the patient. So this is something that will never, I guess, will never change. So like I mentioned here, artificial intelligence is really helping us increase and boost our productivity and make our life easier. So with this, I think that we can sit back, relax, and actually appreciate the quality of the images that cardiac MR provides, and again, bring this exam, so powerful exam, forward in cardiovascular diagnosis for the benefit of the patients, of course. So just a final word on the team. So Eva and Nelson are the engineers, and others, of course, but Eva and Nelson are the engineers that are behind the technology. Of course, that we have other people assisting. Bart Hendricks is also here in the audience, is helping us, reaching out to you and other players around. so that we can, of course, reach to everybody. And Tim Liner, probably also heard of him, is also advising us and giving us help to guide us through the right paths. So this is it. I hope you enjoyed. I think I didn't surpass the time. So I think we still have some time for questions and answers. So I'll stop sharing now.
Thank you so much, Dr. Pereira. That was very, very lucid, and you actually gave us a look into what's also, you know, in the future for artificial intelligence, and cover the entire bit of artificial intelligence in cardiovascular MRI imaging. So Priya, do you have something to say?
Yeah. Dr. Pereira, there are few questions. One of the question was pertaining to abnormal heart, you know. So whenever the right ventricle is really abnormal, like for example, in Epstein's anomaly, or, you know, when the volumes are very important, how would AI-based software would help in that case, do you think?
Okay.
Yeah.
Okay. So the model and every model available will struggle with more uncommon cases and cases where the geometry is less typical, because it was trained with, so the model saw, let's say, 950 cases where the right ventricle had that shape. And so whenever it's abnormal, I mean, extremely abnormal, of course, that the artificial intelligence will struggle, okay? And that's when we jump in and we'll have to correct the artificial intelligence, okay? So that's why I mentioned here at the end that the models are not here to replace no one. We are here to help, but of course that in really abnormal cases, you'll have to step in and correct the model, but it will tell you already, give you a pre-segmentation on top of which you can work on. So it also helps. But and this is very important, in the future, as we increase the number of cases of these, let's say, abnormal cases, the model will get better and better and better. So the expectation is that we can improve this and heading cases, and then it's not needed so many cases. So 100, 200 cases, that abnormal, we can improve the model, and the model will then be very high performing.
Any experience with arrhythmias like frequent PVCs, you know, when
Yes.
systolic and diastolic phases are not synchronous? Yeah.
Yes. Unfortunately, I don't have here a case at end, because so it was very surprising for us to see that the software was predicting very well the segmentation of arrhythmic patients. Okay, we were not expecting that. But it actually, our feeling is that the model works very well when you have premature beats or even in atrial fibrillation. But of course, that the contours are blurred, so the struggle, it's the same for the clinician and for the model, but it behaves well. It doesn't get very upset with that.
Someone is asking about how the software is different from other commercially available software. Is there any specific point you would like to add?
Yeah, so there are, I would say, three main differentiators. One, this model was trained based on real world patients. So this means that we in the model the model is already used with pathological cases like heart failure, ischemic heart disease, cardiomyopathies, and it behaves very well on those pathologies. There are other models that were trained based on healthy individuals. So whenever you have a pathological case, even if it's not that extreme, you will have to go there and adjust. You can see that. So that's one advantage. The data set is unique. The second thing is this interpretation of dual motion. So if you put together the segmentation with the label of dual motion, if the case is normal, you are pretty sure that the case is normal, okay? And you don't see this available with other models. And the third thing is the way we deploy. Since we deploy in the cloud together with the PACS, what happened is that where you have a PACS, you have the results available. You are not stick to a workstation that's only working on a single computer in the hospital. So what was happening to me before, like I mentioned, is that all the cases were in a single computer in all the hospital. So that was even a bit frightening, because if that computer, if we lose that computer, we'll lose all the work. Here is not the case. So whenever you have access to the PACS, you have access to the software and to the results of the software.
Okay. One question is that, is it cross-platform and any implementation of feature tracking?
So it's cross-platform in the sense that we can integrate with any PACS. Okay, so we can work and adjust to with any PACS. We use standard protocol communication. It's called HL7. It's very common in the radiology field. So we use also DICOM format, so it's easy to configure. In terms of feature tracking for strain, I guess that was the question. I showed some results. We are working on that, but we are not making that our priority yet. Why? Because we are tackling the three main sequences in cardiac MR: CNS sequences, LGE, perfusion. So our midterm vision is to get software in place that will make the automatic quantification and interpretation of these three core sequences, and then from there move on.
So from the perfusion sequences, is there a semi-quantitative assessment also is going to be?
Yes, that's what we are planning to do. It's still less developed than, for example, the late enhancement, okay? And still not available. Let me be very clear, still not available. But that's what we plan to do. Okay. Because, so if we go in terms of subjectivity, probably stress perfusion is the one where we got, I think that everybody gets a bit unsure when, and with doubts when appreciating the sequences. So if you have something against with you can compare, that's useful.
Okay.
Just one question, just to make it clear of the workflow of your software. So what you're saying is we acquire the cardiac MR, it gets pushed to the PACS. The images are then pushed to a cloud server where the post-processing happens, and the results are again pushed back into the PACS. Is that right? Is that the workflow that your product is going to give?
Yes, that's the workflow.
Okay, and if we find that the results that are pushed to the PACS are not accurate, or we would like to do any manual changes, how do we do that? So
we have a viewer in place. So you open the viewer, and in that viewer, you'll have the segmentation. You can correct, save, and submit the results again to the PACS.
So this viewer is kind of like a thin client, which can be installed in multiple systems?
Yes, you can call the viewer when needed.
Okay, so it can be, so it's kind of like a thin client which needs to be installed in multiple systems where we need to do the edits or corrections in the processing.
The viewer will be installed either on the cloud itself. So because here the idea is that you can access the viewer from
the viewer
everywhere.
Can be accessed from any browser, is it?
That's it. It's a web viewer. It's a web viewer.
Yeah, it's a web viewer. So we can use any browser to just access the viewer and make
exactly. That's it. Exactly that. That's how it works.
Dr. Vimal has raised hand. Dr. Vimal has some question.
Prof, hi. Thank you very much for your presentation. If I'm not wrong, I understand that the way you have calculated the accuracy of the contour drawing is based on clinicians drawing in your system and the AI drawing in your system. and you have looked at the output if that is comparable or not.
Okay.
Is that correct?
Actually, no. So the experts, so that study that we did with the SCMR data set, the 15 patients, we don't know where the contours were done. So, and we didn't do the analysis ourselves. So we did, the model did the contouring. We sent the contouring to the Society of Cardiovascular Magnetic Resonance, and they did the analysis for us. So that was completely out of our control. What is good for us in terms of benchmarking? The other study that included around 150 patients, so the contours were drawn in a different software, on a third-party software. It was the software that was available in that hospital in Milano, in Italy.
Okay, thank you.
I had a question. So, how long does the post-processing take when it's a web-based,
Okay.
app?
Okay, yeah, that's an important question. So the full process, so sending the images, processing, and getting the results takes around 2 minutes. Okay,
Oh.
so, but of course that if you have to adjust, that's real time. It adjusts real time. But sending over analysis, coming back, it's around 2 minutes. But the idea here is that the moment it reaches the PACS, it goes directly. So ideally, when you sit to see an exam, the segmentation is already there. It's already done. That's the vision.
That's really good. For those who are interested in, AI and deep learning in medtech, I had a question as to how long have you taken, how many years has it taken for you to work on this whole thing and bring it to a product based, to a commercially viable product?
Okay, so if we think of the full time, I would say around 2.5 years. Okay, but let's break this in steps. Okay, so the first thing is to get the clinical data, and to get the clinical data today and correctly, it's harder today because of course that we are more aware of the data protection issues. So it takes a time to get approved by the ERBs of the institutions, and so there's still a lot of time there. Then, and this is the most limiting step, you have to get the data labeled by experts. So you cannot develop a model without experts giving input. And we are all busy. I'm sure that we are all busy. So on top of that, arriving home and then drawing more contours around the heart is not the more exciting thing to do. So having committed physicians to give you the data, the annotations, is a limiting factor, and that can extend well in time. Then training the models themselves, that's relatively fast. And if you have computing power, that can be fast. Okay, so then you get the first results, you are not happy, you go back to the annotations, you correct the annotations, or you increase more cases. But this can be actually pretty fast. And then comes the final step. And the final step here is the also a significant hurdle, is that you have to go through the certification processes. So you cannot put this in the market without having the certification from the health authorities, independently of the region of the globe that you are aiming for. Even FDA, it can be FDA in the States, the CMR in Europe, and the Indian authorities there in India. So we have to go through all these steps. So sometimes you are faster in a specific step, but you get delayed in the other. So it can take more or less time according to that.
Thank you very much.
Dr. Sanjaya has some questions. Dr. Sanjaya?
Thank you, Victor. That was a fantastic lecture. You really took us through the entire pathway of how things are done. I hope all of you can hear me. My questions were sort of more left field than in terms of the exact process. So a couple of questions. Let me ask the first one, that AI is growing. There are new techniques in AI which are being developed even as we speak. So would you say that, and you started off with 1,000 cases initially with regions of interest to build your product, would you say that if somebody was to do the same thing now, they would need a smaller subset, or is cardiac MR complicated enough that regardless of how well developed AI is, you still need larger subsets or larger groups for trial and training?
Okay. Okay, that's a very important question. And if the data set is large, that it's okay. But more important than that is two things. One, the quality of the labels. So if you have if you have high quality label annotations, probably you'll need less cases. Second, you need to have a data set that's representative of the reality. Again, so if you have a small data set, but that data set doesn't have a case of arrhythmogenic right ventricle, you cannot expect that the model will behave well in a arrhythmogenic right ventricle cardiomyopathy. Okay, so have this in mind. You can use smaller data sets, but the quality of the annotations should be perfect. And second, you need to have a really representative data set.
Yeah, so that's a fantastic answer. Thank you for that. My second question was really in terms of who are the people who are going to be looking for AI solutions and who would want to use it. So obviously a very busy practice such as yourself might benefit from this because it saves time. And it perhaps even improves accuracy by saving time, because there's a certain amount of lag which occurs just by repeating the same process over and over again. Would you think that such a model would actually be helpful for places like in India, for example, where we have places which do 10 cases, 15 cases per day, like probably what Dr. Vimaraj does, and even Ashita does a lot. You have intermediate number of cases, like we do about 3 to 6 cases, and you have people who do maybe 1 or 2 a month, or very few cases. So in which group would this work most effectively? And the reason I ask this is, if the bottom line is that you need somebody experienced to look at the images and ensure that the model is doing things correctly, then in a place where with people who are not as well experienced in terms of how to either evaluate fibrosis or evaluate contours, would they still be able to use the information that they get from the model and perhaps give a clinical report?
Okay. Look, I think that's really an interesting question. And we have different perspectives or different lens through which we can look at it. So I think that both will benefit, but will benefit differently. So I think if you take a high volume center, of course, they will boost productivity, and they will take a lot of the burden away from the physicians. And that will be the major benefit for this center. For example, in my case, in one of the hospitals where I work, I have now 2 machines working at the same time doing CMRs, because I can really report more cases at the same time. We have that availability, so it's one example. The small volume centers, I think that they will benefit from having a safety net, a second opinion. Okay, of course, that as a company, let me now talk as a company, we cannot claim that we are as accurate as a physician. We cannot assume that responsibility, let's say, but at least you have there something against which you can compare your opinion with. So, and I'm going to give you a very practical example. One of these days, a colleague of mine had doubts on a case and asked me to review a report I did, because On the ultrasound, the left ventricle didn't seem that normal, and I labeled it as normal. So she asked me, can you review that? Are you sure that there's no mistake on the segmentation? And what I did was that, okay, let me run the case through the AI for CMR. So I got there immediately a second opinion. So you can benefit from that. Of course, that you still need to have some training. Again, we are not here to replace no one. So we want this also to be very clear. You need training, and then the model can help. Of course, that you have to work together with the model. Okay, so I think that you can benefit both ways. In small volume centers, you'll benefit from the expertise of the model. On the high volume centers, I think you'll benefit from the productivity that you can boost.
Thank you. And my last question is with regard to costing. We know that different parts of the world have different reimbursement rates for cardiac MR imaging. India might have one, Bangladesh might have something else, South Africa might have something else, Portugal might have something else. And of course, you have insurance-based regimes such as in the United States, and free places like NIH, perhaps. So when you build your AI solution, are you building it with respect to with the costing at different parts of the world in mind, as well as its efficacy and its usefulness?
Mm-hmm. So we collected a lot of data around the globe, and let me tell you that the price is different even within the same country. If you are in the public sector or in the private sector, and in the private, if you are, it's insurance based or it's out of the pocket. So the heterogeneity is huge, like you mentioned. But here in the cardiac MR field, there's something that we cannot forget, and that's something I always remind. You cannot report a cardiac MR without a post-processing software. So you are always paying something. Even if you say, okay, but I have here an MRI vendor and the software is available by default, you are still paying that software. They cannot put it like this explicitly, but you are paying for that software. Okay, so in our case, it's not that is an add-on on top of something that you already have. No, it's something that you need. So I think that in this case specifically, it's different from other softwares where it's coming on top. Like, for example, if you have a software for the automatic detection of stroke, of course, this will come on top of a workflow that you already have set up. Here is not the case. So this is, you always need this. This is a part of the workflow. So what we are bringing here is that we are bringing AI to this workflow directly without having to be on top of something else.
Thank you.
Yeah. One question from the audience, that since the patient data will be on cloud, I mean, hacking was the issue. What is your thought about that?
Okay, so we host the software in big players in cloud. So either Amazon or AWS in question, or Microsoft Azure. Okay, so these are not our, it's not our cloud, it's not our servers. So we contract big players, and they put all the cybersecurity in place to make sure that we are not hacked. Okay, so this is a big issue for FDA. So we had really to show, because it's FDA approved, that we were safe in terms of cybersecurity to make sure that the hospital was also not at risk. And there's some also very important. We don't keep the cases. So the cases goes to the cloud, it's analyzed, the results go back to the PACS, and the case is erased from the cloud. We never keep data from the cases. The data is immediately erased. Okay, so this is that's definitely a protection. Then, in terms of having a backdoor for any hacker, so actually the cloud is much more safer than having a software that allows an internet connection with a server to validate a license, for example. So the liability there is bigger. So actually, on the contrary of what many people think, me included, when I started, the cloud is safer than actually running software on-prem on your servers. You expose more yourself if you run things on-prem than over the cloud, if you are using, of course, a top cloud provider.
Dr. Rajesh is also your, sir, any questions, any thoughts? So for all the users, you can meet this company people during our annual meeting in Coimbatore. They are going to be physically present, and probably you can experience, have a first line experience of the software. So if you have not registered, please register for the meeting, and see you in Coimbatore. Thank you, Dr. Vitor, Ashita. Yeah, it was really a great meeting, and hopefully we'll meet soon. Yes, yeah. Thank you, everyone. Good night.
Thank you. No, thank you. It was a pleasure being here, and thank you so much for the questions. Really valuable questions. Thank you. Bye-bye.
Bye.
Looking forward to the national conference. Thank you, Dr. Pereira. Good night.
Thank you, Ashita. Bye-bye.